Hoş geldiniz. Welcome everybody. It's a great pleasure to welcome Jocelyn Bell Burnell here. Dame Jocelyn is the discoverer of pulsars. For the astrophysicists among you, pretty much everyone in astrophysics in Istanbul is present here. She started our field. And she went on to contribute in several different areas of astrophysics. She's a very prominent outreach person, popular speaker, and she's also currently the president of the Royal Society of Edinburgh. I'd like to welcome you, Jocelyn.
Thank you very much, Harley. Thank you. Good afternoon, ladies and gentlemen. Thank you for being here, and thank you from me for the opportunity to be here. I love this city. It is looking so good today. It is great to be here with all of you. And I also want to give thanks to Professor Alpar for the Turkish captions on the slides. So if you do not understand my English, there is a Turkish summary. Not as full, but at least something. So this afternoon, I want to tell you how pulsars are now challenging Einstein's theories of relativity and gravitation. I will also tell you a bit about what pulsars are themselves. They are really quite amazing, I think. Okay, we have a range. Right, so this afternoon I will introduce pulsars, and I will after that talk about testing Einstein's theories. So if we start with the pulsars. Pulsar stands for pulsating radio star. These are objects that radio astronomers look at. They are usually not seen with ordinary telescopes in the visible, in the optical, with our eyes, mainly radio. Imagine you have a lot of satellite TV dishes, 2,000 satellite TV dishes. You connect them up together with some very good cable. You plug them into a very good radio receiver, and you move them to look at a particular bit of sky. And then you listen to what the radio telescope, the satellite dishes, are picking up. And if this works, you might hear something like this. Maybe you won't hear. It sounds a little bit like a truck, a tractor that needs some maintenance. The engine in a tractor or a car idles when you are not moving at that rate, about 700 revs per minute, 600, 700. That's why this sounds like a truck, a car, a tractor. But it is not. I wished at times it was, but it is not. It is a star. It's a star with a mass of 1,000 million tons, 10 to the power 27 tons. And it's all spinning on its axis 11 times per second. 11 times per second is 660 times per minute, which is close to the 700 that the engine idles at. So it sounds quite like an engine, but it is actually extremely massive and spinning very, very fast. That is a pulsating radio star or a pulsar, one of them. The picture we have looks like this, and I'll start with the right-hand picture. We have a star spinning, and down here, dim, 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 flash, dim, 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 dim. Again, whee. As the star spins, a bit like a lighthouse, it sweeps a beam across the sky, and every time it falls in our faces, we see pulse, pulse, pulse. Only that one was going 11 times a second, which I cannot do. And this on the left is another picture. Here is the star, the 1,000 million tons. It's spinning about an axis here. Do you know that on Earth, the magnetic North Pole is not at the true north? The magnetic North Pole is in North Canada. It is offset from true north. Similarly, on a pulsar, there is true north, there is magnetic north. This is the magnetic pole, North Pole, South Pole, magnetic fields of lines of force, and over the poles, the magnetic field lines make this shape of a cone, a funnel. And somehow, we still do not fully understand how, a beam of radio waves comes out here. And as the star spins, the beam swings around the sky. Depending on how the spin axis is tipped, I'll show you with the laser. Sometimes, will I show you with the laser? Maybe it's too faint. Sometimes the beam goes round like this, and we never see it. Sometimes it goes round like this on other pulsars, and we can see it. We see about 1 in 5, probably. The other 4 out of 5, their beam does not shine on the Earth, so we never see them. Just to give you a little bit of context, I have said these are stars. How do they fit with other stars? I'm going to concentrate on big stars, massive stars. Stars that are maybe 10, 20, 30 times the mass of our sun. Our sun is a very ordinary star. We're focusing here on the heavy ones, the massive ones. And an example of such massive stars is the group of stars, Can we kill some lights here? Take these lights down? Maybe we can't. There are a nice group of stars here, the Pleiades. You can see them in the winter sky. They're one of the delightful things. We're getting better. We'll see. Maybe we can do it. This group of stars is a young group. They're less than 100 million years old, and that is young for astronomy. They are massive, and because they are massive, the temperature in the center is a little bit higher than it would be in less massive stars. And because the temperature is higher, the reactions go faster. Inside these stars, there are nuclear reactions that release energy. They are exothermic. And stars that started with just hydrogen end up with iron and nickel in their centers, in their cores. This is bad news for the star, because iron and nickel are not exothermic. You can never get nuclear energy out of iron or nickel. They only absorb energy. And when the star gets to this stage, after, say, 100 million years, it has a crisis, a life crisis for a star. There's a complicated set, thank you, that's much better. There's a complicated set of reactions take place. I show you two photographs here. In this one, I'll start with, you maybe see some pink-red material. That is hydrogen. Hydrogen has a red spectral line. And there's hydrogen everywhere. It's the most abundant element. So in any astronomical photograph, when you see red stuff, you say, ha, hydrogen. And you will be right 95% of the time. You now know 95% of astrophysics. Not so clear in this picture are lots and lots and lots of little faint stars, and one of them is picked out with an arrow. To be absolutely clear, the arrow is added after the photograph is taken. There are not arrows in the sky pointing to interesting stars. But look at this corner of this photograph. This is the star that was so small and inconspicuous that we had to have an arrow pointing at it. It has exploded. It has got to the stage where it's had iron and nickel in its core. That is endothermic, not exothermic. It leads to a crisis. The core collapses and the rest of the star explodes. And we see here the exploding material. The core of this star is still there. It has been squashed and shrunk, and it's now one of these pulsars, also known as neutron stars. And it weighs, has a mass of 1,000 million tons. It's set to be a pulsar. So the pulsars are created in the explosions that mark the end of the life of some big stars. They are a form of life after death of a star. This is the remains of a star that exploded about 1,000 years ago. It's known, at least in the English-speaking world, as the Crab Nebula, because with early telescopes, it looked like a crab with lots of legs sticking out. There is a pulsar about here, and the discovery of this pulsar solved a mystery. The mystery was, why does this keep shining? It's 1,000 years since the explosion. Why is it still shining? And the answer is, the pulsar keeps it shining. The pulsar provides energy that keeps the Crab Nebula shining. For those interested in the technicalities, it is synchrotron radiation. So the origin of pulsars is in the big, massive stars that explode at the end of their lives. What can we say about the pulsars themselves. I've already mentioned the mass, 1,000 million tons. They have a radius of about 10 kilometers. And that is not a mistake. I do not mean 10 to the power 25 kilometers. I mean 10 kilometers. We have 1,000 million tons all in a ball with radius 10 kilometers. Imagine what would happen if somebody set one of those down on Istanbul. Maybe here we would be okay. Are we far enough away from the center? Bit uncertain, yeah. There'd still be the gravity, which you need to watch. So the density of these objects is huge. It's like the density of the nucleus of the atom. And as I've already mentioned, these things are sometimes called neutron stars because they're rich in neutrons. Saying it has a density like the density of the nucleus, that doesn't help. Who has met the nucleus of an atom? However, I have an analogy. Take a thimble, a sewing thimble, preferably a nice silver sewing thimble. Take the population of the world, 7 billion people. Squeeze them into the thimble, one after the other. And when you have all 7 billion inside that thimble, it weighs the same as if it were filled with material from these pulsars or neutron stars. That's what the density means. Because we have a lot of material in a very small volume, there's very strong gravity at the surface. And if you were to climb a mountain on the surface of one of these stars, the mountain has only to be 1 micron, 1/1,000,000th of a meter high. And the work you would do climbing up that micron against the local gravity is like climbing Everest here on Earth. And because of the very strong gravity, the atmosphere is collapsed. In the absence of electrical magnetic forces, it's collapsed to about 10 centimeters. So if I were standing on one of these stars, the atmosphere is down around my toes, and in order to breathe, I have to get my nostrils down there. We would be different shapes if we lived on these stars. Gravity also bends light, and the gravity is so strong that I can stand on the surface of one of these stars and look around. I can see over the horizon. I can see 20 or 30 degrees over the horizon, and so without moving can see about 2/3, 3/4 of the surface of the star, because the way gravity bends the light. And gravity also affects clocks. So, for instance, if I, at great danger, take a big clock and go to one of these pulsars, and you stay here on Earth, where the gravity is less, with a big telescope, so that you can read my clock, you find that my clock does 1 tick every 2 seconds. Tick, 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 tick. I can take my pulse with my clock. It's okay. What do you mean my clock is slow? My clock is okay. But the strong gravity has not only slowed my clock, it has slowed my heart and my metabolism and my brain. So I think it's okay. But you, in a low gravity environment here, know that it's certainly different from Earth. So gravity affects clocks and hearts and brains and metabolism. There is also a very strong gradient of gravity. Suppose I am coming in to land on one of these stars. The surface is down there, and I'm coming in feet first, because this is the ladylike way to land on one of these stars. And as I come down, I'm pulled by this very strong gravity. But there is more gravity on my feet than on my head, because there is a gradient of gravity. And the result is my body gets stretched long and thin. Do you have spaghetti in Istanbul? Okay, the technical term for this is spaghettification. Unfortunately, the difference in force between my feet and my head is so strong, not only does my body get stretched, it gets pulled apart. And even if I curl up as small as I can, the difference in force between the bottom and the top of my body pulls me apart. So do not go visit a neutron star or a pulsar. You will not survive. It also seems that pulsars have very strong magnetic fields. We think, typically, 100 million Tesla. To put that in context, your fridge magnet is about 1/100th of a Tesla. And a physicist would be pleased to have a 10 Tesla magnet in their laboratory. We don't understand how these magnetic fields are made, but we know that they are bigger and last longer than humans can make magnetic fields. And you remember I talked about the star spinning? If you spin a magnetic field, you get some very, very big voltage drops, 1 billion volts in a centimeter. So don't take your credit cards to a pulsar. And all that apparently rotates like a solid body, as one. We think that the pulse period that we see is the rotation period. The fastest pulsar we see has a period of about 1.4 thousandths of a second. The slowest is about 10 seconds. Now, think of a military demonstration. Soldiers are marching. There's a long line of soldiers, and they march, they keep the line. But when they have to go round a corner, the guys here are not moving, and the guys out here are going, trying to make it look easy. They have to walk very fast. If you have a pulsar that's spinning with a period of 2/1000th of a second, by the time you get out to the surface of the star, it's going much faster. And indeed, by the time you get out to about 200 kilometers, you're traveling at the speed of light. And nothing can go faster than that. So these things are seriously relativistic. Einstein's theories of relativity cannot be ignored when you study pulsars. They're too extreme. I have mentioned how these objects are seen with radio telescopes. We know of about 2,000, but only about 20 of those can be seen with ordinary telescopes. And it has to be really big ordinary telescopes, usually, to see them. We can see them with X-rays, and surprisingly, we see a lot with gamma rays as well. Now, our sun is a star. It's a very ordinary, average star. With one exception, it seems to be alone. Many stars are in pairs, but the Sun does not seem to have a companion star. Most stars do, and we find some pulsars, about 150 pulsars, that are twinned with another star. They are dancing around each other. We have found one pulsar in a triple system where there are 3 stars, a pulsar and 2 others. I'll talk about that a little bit later. And we found a few with planets, which is also a little curious. We think there are about 100,000 in the galaxy, in our galaxy, but similarly in other galaxies as well, probably. They are quite weak emitters of radio waves. You need a big radio telescope or 2,000 satellite dishes to be able to pick up the signal. But one interesting thing is their mass, 1,000 million tons. When you get 1,000 million tons spinning, it keeps spinning. And the beam comes round very regularly. They are very accurate. They are good clocks. Indeed, they are such good clocks that since the age of the dinosaurs, a typical pulsar's period would only have changed by about 1 second. Nature has now given us clocks dotted throughout the galaxy, which allow us for the first time to do tests of Einstein's theories in a much, much better way than we could do here on Earth. And that's one of the themes that I want to follow up. I'm going to start by talking about gravitational radiation. I'm going to say more about this than I would normally have, because the astronomy rumor mechanism is working very, very well. And we believe, well, the rumors tell us, that on Thursday of next week, there is going to be a major announcement about gravitational radiation. So, assuming the rumor is correct, in preparation for next Thursday, I'm going to tell you just a little bit about what gravitational radiation is. It is part of Einstein's theories, and Einstein said that you can have waves or little waves called ripples in space-time. This is a little bit hard to picture. Space-time has 4 dimensions, 3 of space and 1 of time. Normally, we only draw 2 dimensions. And here in blue, we have 2 dimensions of space-time, so it's like a sheet with ripples on it. And these ripples are representing gravitational waves. The ripples in this case are caused by a pair of stars in the center that are moving closer together and will one day merge. They are what's called transverse waves. They travel at the speed of light, and in case you're interested, they carry energy, momentum, and angular momentum, but that's a bit specialist. But basically, imagine you have a very good mattress on your bed at home. The surface of the mattress is like space-time. 2 dimensions of space-time. If you put something heavy on your mattress, the mattress forms a little dip. So out here the mattress is flat, and then it dips where you have put down the heavy suitcase or the bottle of water or what have you. Now imagine you take this heavy weight and you move it up and down on the mattress. Then you could imagine that there would be waves moving out and gradually disappearing as you go out across the mattress. It's a bit like that with space-time. Something is making ripples, and they travel out. And in this particular illustration, it's a pair of stars going round each other. One of the nice things about gravitational waves, in contrast to light and radio waves and X-rays, is they're not absorbed, they're not scattered, they just go through. I'll skip the next few lines. They're fairly technical. There's a whole range of gravitational waves. I've talked about a pair of stars orbiting and giving it. It could be a pair of stars, or you might be dealing with a pair of galaxies, which quite often have really big black holes at their middle, and the galaxies are merging and moving in. But I'll concentrate on a pair of stars, a pair of black holes orbiting each other. Einstein says that where you have two things orbiting each other, there is this gravitational radiation. So there's the gravitational radiation going away. The gravitational radiation carries away energy. When you have a pair of stars orbiting each other, if they lose energy, they move closer together. When they're closer together, they go round faster, there's more acceleration, so there's more gravitational radiation. So the pair of stars lose more energy, so they move even closer together. They go round even faster, and there's more gravitational radiation. And ultimately, the two stars merge, and there's kind of a whoosh of gravitational radiation. And that's true whether you're talking about stars merging, black holes merging, supermassive black holes at the centers of galaxies merging. And there's this characteristic pattern that starts off with a little, getting bigger, and going whoosh at the end. And that's what the gravitational wave astronomers are looking for. And if the rumor is right, they have found it. If there is a whole range of frequencies that the radiation can have, there's a range of ways we can pick it up. This picture on the right is the one you might, big hint, like to concentrate on particularly. It is a ground-based detector. There are a pair of them in the United States. They're called LIGO, Laser Interferometer Gravitational Observatory. You could do something similar from space with satellites. You pick up a slightly different frequency. That's still in the future. And you can use pulsars, which is why I'm talking about this today. And there's a race on between the pulsar radio astronomers and the ground-based LIGO, and we'll know next Thursday, maybe, if somebody has won that race. I'm going to say just a little bit more about the pulsar timing. Yeah, right. Here we have the Earth. In the green we have space-time. And here we have a whole lot of pulsars dotted around the sky. These pulsars are good clocks. And I'm going to give you a little demonstration, which will mean my microphone needs to go off. And we have a microphone over there. Can you hear the pulsar? It's my kitchen clock, but it's a pulsar. If the pulsar is moving, could you hear the Doppler Shift, a change in note? Yes, thank you. When the pulsar is moving towards you, the pulses pile up. The space between them is smaller. When the pulsar is moving away from you, the pulses are more separated, the period is longer. For the physicists in the audience, I am cheating. You heard a Doppler shift, which is what this is called, but it was a Doppler shift on the note of the timer. If the timer had been a continuous note, you would still hear the Doppler shift. However, it's not bad as a demonstration. Right, another round of this. Could we have my microphone off? So now we have Einstein's theory. There's gravitational radiation going off. The two stars are moving closer together. The pulsar speeds up and up and up and up and up and up. And finally, there is a merger. And throughout that process, if Einstein is right, there'll be gravitational radiation coming off, getting faster and faster. And if you have pulsars all round the sky, then it's actually the Earth that is moving, but you still hear the change in the period. So I think we are close to an announcement about gravitational radiation. We will see next week, to be honest. I have said most of this. I have talked a little bit about how pulsars can be in pairs. We know of a lot of cases of a pulsar with an ordinary star. We know of a few cases where both the stars are neutron stars. And we know of one case where the pulsar is twinned with another pulsar. Now, studying the orbit of a pulsar is easy. And way back in 1974, two US radio astronomers found a pulsar that was orbiting another star. They also found that the orbit of the pulsar was changing because this pair of stars was emitting gravitational radiation. And they showed that the way the orbit was changing was exactly consistent with Einstein. So this graph, it has date along the bottom, and up here is one of the parameters of the ellipse, of the orbit. And the black dots are the data. People near the front can perhaps just see some error bars, but quickly their technique got better. By here, the error uncertainty is about 20% of the size of the dot. The line is not the best fit. The line is Einstein's prediction, and it's beautiful. They have shown that the way the orbit of the pulsar behaves means that Einstein's prediction is correct to within 0.33%. That bit of general relativity looks very good. Then, more recently, we had a case of where there are two pulsars that we see orbiting each other. We only have one example of this, but it's a very good example because the two stars are very close together. They orbit each other in under 2.5 hours. So the size of their orbit is half the sun's diameter. And because they are so close, they're going around very fast. Relativity matters, high gravity, high speeds. Physicists' nightmare, but wonderful if you like this kind of thing. This is the most relativistic system we have so far discovered, and it's being used to check out other bits of Einstein's theories. A reminder about orbits and ellipses and Kepler's theories. if you have two stars widely spaced, they go round each other in orbits that are elliptical. And if you have studied ellipses, you know that to specify an ellipse, you need the period, the length of the major axis, which is this, the eccentricity, how circular, how non-circular is it, and two other quantities called the longitude and epoch of the periastron. That's fine. That's not too bad. That's only 5 things you have to find out. But if the two stars are very, very close and relativity theory matters, there are another 5 things you have to measure, 10 things in total. And one of the things is, if I go back a slide, the ellipse moves round. So I try a demonstration. You make an ellipse, but if it's relativistic, the ellipse moves round, and the ellipse moves round, and the ellipse moves round, and it makes a flower, a rosette shape. And one of the quantities you have to measure is how quickly does it go round the rosette, the advance of periastron. So advance of periastron is one of the things we have to measure. Do you remember me talking about clocks going slow? That's gravitational redshift. That's another thing we have to measure. The orbital period changes. Do you remember the demonstration where it got faster and faster and faster? And then there's a couple of other parameters. So there's 10 quantities we need to measure. And with the double pulsar, we have measured them all. Not me personally, but they have been measured. And indeed, we're getting beyond that now, which is really very interesting. If you're into this kind of thing, they've also measured the precession due to relativistic spin-orbit coupling. And we hope soon to get an independent measure of the moment of inertia of the stars, which would be really useful. The system is now over-constrained. We've got 5 independent tests of general relativity. And the best way to demonstrate this is with a graph. So we make a graph showing the mass of one of the stars against the mass of the other stars and plot on it all the parameters we've got. And if Einstein's right, they intersect in a point. So mass of one star, mass of the other star, you can just about work out which of these parameters of which. S is one of the Shapiro ones, R is the other Shapiro, PB dot is how the period changes, omega B is precession, and so on. And it looks good. You blow it up a bit, and you see there's a very, very small blue shape where they work. And at the moment, they're still working on this, they're pushing even harder, but at the moment, the theory's okay to within 0.02%. These are the theory of gravitation in particular. There are a number of other theories. They're really having a very tough time, these other theories, and it's going to get more and more interesting as they beat this limit down. One of the reasons for pushing on this is we really want to be absolutely sure that Einstein's theories are right, because we have an issue in physics, an issue about fitting together the different bits of physics. And gravity is one of the bits of physics that won't fit with everything else. So maybe at some level our understanding of gravity is wrong. Maybe at some level Einstein's theory of gravity is wrong. I'm going to talk, there's really just a few more slides now, very briefly about testing the strong equivalence principle. This is another aspect of Einstein's theories. For the physicists, there's weak equivalence principle and strong equivalence principle. What these things measure is strong. Weak has already been measured and shown to be quite good. The most famous test, or the second most famous test of equivalence principle, is where you drop two different things. Galileo first tried it. He dropped a feather and, can't remember, stone or something, off the Tower of Pisa to see if they landed at the same time. They didn't, because the air resistance made the feather go down like this. So the stone's already down there, and the feather's still wafting its way down. The atmosphere stops a proper test. But it's also been tested by US astronauts on the moon. The first one was Apollo 15, where Dave Scott had a hammer and a falcon's feather. There's no atmosphere, or very, very little, on the moon, and he dropped them, and they both landed at the same time. But because the bandwidth was very, very narrow when Dave Scott did that, there's not a good picture of it. So the astronauts did it again. And this is the most famous repeat. And he's just dropped the hammer and the feather. And it does look like they're falling at the same rate. There are other tests that you can do of the weak equivalence principle, solar system tests. And we know it's good to 1 part in 100 million. It's pretty good. But that's weak gravity. To test it in strong gravity, that's more difficult. But we've recently discovered a pulsar in a triple system. There is a pulsar twinned with another star, a white dwarf. They orbit each other, and the pair are orbiting around another white dwarf star. So you can think of the pulsar like the hammer, this white dwarf as like the feather, and they're moving under the gravity of this star. And do they move in the same way? Do they feel the same gravity force? If they do, then the orbit of these two stars round each other will remain unchanged. But if they feel different forces, then gradually the orbit of this pulsar and the other star will change. And you know from this demonstration that measuring changes in orbits are easy. Radio astronomers can do it with phenomenal accuracy. So this is a relatively new discovery. We don't have the answer yet. There is not sure if she's a postdoc or a graduate student working on this. And on Monday she said, oh, this is terribly exciting. It's so important. And then on Tuesday they said, oh dear, I'm so stupid. And then on Wednesday she said, no, it's really, really exciting. And on Thursday she says, oh dear, I'm stupid. And I don't know what the answer is going to be. The one intriguing thing is one of the predictions, if I go back a slide, one of the predictions is that the orbit here of these two, if it is elliptical, then the long axis of the ellipse points this way. And she says the long axis of the ellipse points that way. But she hasn't been able to sort out any change in orbit yet. So this is work in progress. It's another case where the rumor system is working very well, but we have no definitive result yet. It could be that we found violation of the principle of equivalence. Or maybe we haven't. We'll see. So by way of conclusion, Einstein's theory has stood up to all the tests we've been able to do. It stood up with quite high accuracy, but the pulsar astronomers are continuing more and more stringent tests because, as I've alluded to already, there are problems meshing gravitational theory with the gravitational force with the other forces. There are issues with what professionals call singularities, that's black holes, basically. And there's a hunch that at some level, maybe the theory of gravitation is wrong, needs some modification, inadequate. We will see. Time will tell. But I think that's enough for now. Thank you for your interest, and thank you for your patience.
We will now have a question and answer period for 15 minutes, and then we can continue the discussion downstairs, where tea and coffee will be served. And I'd like to thank Jocelyn again and present her with this little souvenir.
Oh, the poster. Thank you.
You can take the questions directly yourself, right?
Right, will you watch the time? Will you say when was the last one? Right. Okay, so...
we have two helpers, Sinem and Onur, with the microphones. Yeah, Sinem, you can go on that side.
So if you raise a hand, a microphone might come to you. Question? Yes, there's somebody close to this mic. No, behind you. Behind you, sir. Back. Back. A small person.
I would like to ask you something about the pulsars. Why did you name them with little green men? Because the pulsars are actually some neutron stars, and they glow as blue, so they are not yellow. They are not green, and I don't know the reason for doing that. Can you explain it for me, please?
Yes. Thank you. Lovely question.
Thanks.
When we first found this curious signal, we did not know what it was. And it took me about a month before even I realized it was regularly pulsed. And I could have called it in conversation, you know, that funny source at right ascension 1919 and declination somewhere between 20 and 23. But that's rather a long name. So as a nickname, and not seriously, I labeled it Little Green Men. And you can now find that, because I found 4 pulsars, Little Green Men 1, Little Green Men 2, Little Green Men 3, Little Green Men 4. 4 is many, too many. 2 is too many. 1, yeah, probably not. But it was a nickname, and I was not serious. And I now regret the name, because it will not go away. Thank you for a very good question.
I have read the book from Stephen Hawking, A Brief History of Time. There was a part that mentioned you. He was saying, you thought you communicated with aliens. I've forgotten what I'm going to say.
I think that you thought you communicated with
So,
aliens.
Did you really think that you communicated with aliens?
No.
So
No.
it was just a joke then.
There was about a month between finding the first one and the second one. And during that month, we were trying to find what was wrong because the signal was so peculiar. But when you find a second one in the different part of sky, there are not going to be 2 lots of aliens, both signaling to planet Earth. Why Earth? Why at 81.5 megahertz? And why using amplitude modulated signals? They are stupid, crazy, if they exist. It's all too stupid. It cannot be aliens. So we did not ever believe it was aliens. It was just, unfortunately, a bad joke on my part.
That's so bad.
Hold a second, gentleman by the aisle. There's one further back. Yes, sir. There's a microphone. We'll take the one at the front and then we'll come further back. Yes, sir.
Okay. If you had a chance to give 3 advices to today's science students, physics students, especially women, what would it be?
In slang, it is hang in there. Do not give up too easily. Keep trying, and you will fly.
Thank you so much.
Is this microphone?
Yeah, thank you really much. I would like to thank you for this excellent, extraordinary presentation. I have 3 questions about related with your presentation and one with some other topics. In one of your slides, I have observed a beam of ray that crosses like a what's the name? Like a sword, a beam of sword. Yeah. Is there any particular reason why this kind of shape is observed, or is it because of an explosion of a star?
No, the ray is meant to represent the radio beam. The radio signal is a narrow beam, and you see flash, flash, flash. And we do not fully understand how it works, but we think the magnetic field of the pulsar makes the small beam, like a laser.
Yeah, okay. Thank you very much. The other question is, let's consider a pair of a pulsar. They are orbiting each other. Do they orbit each other like a circular shape, or they, let's say, orbit each other in an ellipse shape? Or
Yeah. Yes, they are both in ellipses. It's quite hard to. It's a bit like that. Yeah, the 2 pulsars have very similar mass, so the 2 ellipses are fairly similar.
Okay, thank you very much. The other question is a bit out of the topic. Maybe 1 or 2 months ago, there were a huge discussion between the astrophysics. They observed one of the stars that is, let's say, I can't particularly remember the quantity, but the sun in the first observed maybe 20 years ago, earlier than this time, it was shining quantity, and a couple of months ago they observed another shining quantity which is 30 or 25% decreased, and they say this is it can be because of extraterrestrial life. What do you think about this? What would you say?
I think there are many natural reasons that we need to explore for this kind of phenomenon before we think about extraterrestrial life. It's very, very probably natural, not aliens, not little green men.
Okay, thank you very much.
Is there one? Yes.
You have shown us how 2 pulsars affect space-time with their gravitational waves, and I would like to ask that how would they behave if our universe had 4 dimensions of space and 1 of time? And also, why do you think we have 3 dimensions of space?
The 3 dimensions of space are quite easy to explain. You can imagine axes, one going that way, one going that way, and one going that way. And then there is time as well. So 1, 2, 3 plus time makes 4. That's the world that we seem to live in. There are theories around that say, some string theories, that say we live in a 10 or 11 dimensional space. So there's the 4 that we are aware of, the 3 space, 1 time that we are aware of, and many others that we human beings are not aware of, but do exist. It's a bit hard to do science on things that you can't see and measure. But so the current understanding is that we do indeed live in a 4-dimensional space, but there are suggestions that there are other dimensions.
But why do you think the third dimension overcame the others? Like why antimatter fall under normal matter?
The dimensions I'm talking about are dimensions of space and time. And it's not a case that one has overcome the others. They are actually interleaved, particularly when you get into relativity theory. When you get extreme conditions, then you get phenomena that seem curious to us because the time and space dimensions get mixed up. But I wouldn't want to say that one overrides the other.
Thanks.
Can I ask? Okay. According to the Einstein's theory of relativity, it is famous equation E equals mc squared. In any other situations, the same situations, if we take the C as 1, then we're left with E equals m. Therefore, we say that energy equals to mass. In other case, if we try to do a spaceship which goes as fast as the speed of light, and then we need infinite push to make it equal to energy to the mass. To make it, it's just my thought, to make this push, to support this push, can we use antimatter just like that? If we demonstrate the experiment of Young, Professor Young, as double split experiment, if we send all the antimatter to the double split, then make them get together in a different phase, therefore it can neutralize the matter. So we can say, we can actually put these same things just in a box, so we can contain those things in a box. Therefore those can neutralize each other, therefore we can support the energy. If we need this energy and if we go deep space, then we can make this experiment again. We can put these, we can send those antimatter which combine in a different phase, and therefore we can send those and they get together in the same phase, and then they can neutralize each other, and so we can support this energy, so we can go to the deep space. You think that this is possible or impossible? What are your opinions?
I think there are enormous difficulties. Your box in which you keep the antimatter.
This is just a thought. You know, this is a mechanism. With box, I'm just saying this. This is actually a mechanism that you can combine those in a spaceship or in a cabin. So it's just a saying.
You have very big difficulties about how to handle the antimatter. Your slits, for instance, cannot be made of matter. Your box cannot be made of matter. So you have big questions about how to corral the antimatter. And then it's very high risk, because if matter and antimatter get together, a blast of gamma rays. So I really doubt we could make it work in practice, I'm afraid.
Okay.
Thank you for the speech. I'm assuming that you were referring to the unified theory, the apparent contradiction between quantum mechanics and Einstein's theory of relativity. Would these observations, if prove that Einstein is still correct, would it prove that gravity is not a force like the rest of the others, but is simply a result of the properties of space-time? Because I think it was Stephen Hawking who said that he is getting more and more doubtful about a unified theory. But I mean, would there be ever a resolve to this question, whether there is such a thing?
I think the answer to that is no, because of what we actually show when we do science. If we show that Einstein's theories are still good, then we have only proved that they are good as far as we have got. And, you know, you have to go better and better and better before you can make the large kind of statement that you're making. And I'm not sure that philosophically we could actually ever make that kind of large statement. What tends to happen in science, what's happened with black holes, for instance, it's very hard to prove that there is a black hole in Cygnus X1 or wherever. What has happened there is people said, well, it could be a black hole, and other people said, yeah, but it could be a triple system or a quadruple system or a da-di-da-di-da with wings on it, you know. And people get tired of dreaming up alternatives to the black hole picture. And after 20 years, they say, well, I suppose it is a black hole. And you proceed on that assumption. But it has not been proved. You can disprove things, usually relatively easily, but proving something is much, much harder. And usually the community spends some time trying to disprove and then says, oh, well, I suppose so. But it's not proof. Center of the front.
I'm here again. What do you think about today's science community? Do you think that actually it gives the equal chance to women, or is there still more improvement to do?
Right. I'm really impressed the number of women here. It is better than in an audience in Britain, where you might get 20% women for a science talk. Interestingly, I also do talks on astronomy and poetry, and there my audience is more women than men. A totally different audience. The situation has, in places like Britain and the US, has improved enormously for women since I was a young woman. It's got a lot better. It is still not perfectly fair, but it is getting better, and we understand better why it's not fair. It's something called unconscious bias. How many people here have heard of unconscious bias? A very few. I will give you an example that is not from science. We have an orchestra. We want women and men to play in the orchestra, but it seems that men more often get appointed. So we set up a new system. We have a screen. So you who are selecting for the audience can hear the candidate play their violin, but you cannot see whether it is women or man. And orchestras that do that now have lots of women, as well as lots of men. Both women and men, if they make a very quick judgment, think the man is better, because they are a man. That's what we mean by unconscious bias. Everybody does it. We must learn to compensate for that quick decision and take a more careful decision. And certainly now in Britain, in universities, as of about 1 year ago, people are getting training about unconscious bias, and they know to look at the numbers of men and numbers of women they are selecting and try and make sure they are even.
Thank you so much. You are a huge idol for this century in the sense of physics and also in the sense of this social understanding. Thank you so much.
Thank you. Thank you.
I guess we can call the session ended, but we can continue the discussion
Over tea. Yes. Thank you. Thank you very much.